So let V be a finite dimensional vector space with the basis, let's say the dimension of V is n, with basis E1, E2 up to E sub n. So this is an ordered basis for the vector space V. Let W be another finite dimensional vector space. Let's say the dimension of W is M, with basis F1 up to F sub M. M and M can be the same or they can be different. And suppose we have a function T from V to W, that T be a linear transformation. So that's a special kind of function between vector spaces. That means it has the property that T of V1 plus V2 is T of V1 plus T of V2 for all vectors V1, V2, and V, and T of C times V is CT of V for all vectors V and V, and C in the field F. C is a scalar. So a linear transformation from one vector space to another is a function that satisfies these two fundamental properties. These are very, very, very important. And every linear transformation between finite dimensional vector spaces can be represented by a matrix. And the way we do this is as follows. So for every j from 1 up to n, E sub j is a basis vector for V. So T of Ej is in W, because T maps V to W. And so T of Ej is some linear combination of the basis vectors in W. This is summation, say, Aij f sub I goes from 1 up to m. And so as j goes from 1 to n and I goes from 1 to m, we have these numbers, these scalars. And let Aij be the m by n matrix. So I goes from 1 to m, j goes from 1 to n. That defines a matrix A. And what is the connection between the matrix A and the linear transformation T? So again, T of Ej is summation Aij f sub I goes from 1 up to m for all j between 1 and n. Again, we always have this picture. Here's V, here's W, and T is a function from V to W. Suppose we let V be a vector in V. So then V is some linear combination of the basis vectors, summation xj ej, j equal 1 up to n. The ej's are form a basis for the vector space V, so the coordinates x sub j are unique, and we have the coordinate vector for the V with respect to this basis that we call it E. It's just the vector x1, x2 down to x sub n. And suppose we have T of V is a vector in W. So T of V is some summation yi fi. I goes from 1 up to m. And the coordinate vector for T of V with respect to this basis f for W is the vector y1, y2 down to y sub m. So I'm going to show you the relationship between these two coordinate vectors. This is in Rn, or Fn. This is in Fm. What is the relation? Well, it can go as follows. You see, what is T of V? T of V is T of summation xj ej. J goes from 1 up to n, because V is equal to this vector. Because T is a linear transformation, this is summation, j goes from 1 up to n, x sub j, T of E sub j. This is T of E sub j. Summation j goes from 1 up to n, x sub j. T of Ej is summation I goes from 1 up to m, aij, f sub I. We can interchange finite summations. This is summation I goes from 1 up to m. Summation j goes from 1 to n, aij, x sub j, f sub I. So here I've written T of V as a linear combination of the f's, and these are the coordinates. So if I look at the coordinate vector for T of V with respect to f, that is, these are the coordinates. Summation a1j xj, summation a2j xj, down to summation a mj xj. J goes from 1 to n in all these sums. Now, if you take the matrix A times the vector x1, well, let me do it like this. More space. If I take the matrix A, this is an m by n matrix, times the vector, the coordinate vector for x with respect to E, which is an n by 1 matrix. So this product is m by 1. What is this? This is the matrix A, A11 up to A1n, AM1 up to AMN, applied to the vector x1 down to xn. And when you perform this matrix multiplication, the first coordinate is summation a1j xj. J goes from 1 up to n. The second coordinate is summation a2j xj. J goes from 1 up to n. All the way down to the nth coordinate, which is summation, the mth coordinate, a sub mj x sub j. J goes from 1 up to n, which is exactly the coordinate vector for T of V with respect to F. So we come to this following very beautiful theorem. You take this matrix A that I defined, the matrix of the linear transformation with respect to the bases E and F, A applied to the coordinate vector of E, you just do ordinary matrix multiplication. This is the coordinate vector T of V with respect to F. So this formula, if you understand what all the symbols mean, explains how you can represent a linear transformation by a matrix. You have a linear transformation on finite dimensional vector spaces. You fix bases E and F for the vector spaces. You look at this matrix A, which comes from, again, how do we get A? A, we have that T of the vector EJ is summation AIJ F sub I. I goes from 1 up to M. This is how you get the coordinates of this matrix. And if you look at this matrix, let's see, what is the jth column? I have A1J, A2J, down to AMJ. Right? This is A1J F1, A2J F2, A3J F3 to AMJ FM. The jth column of the matrix is the coordinate vector for T of EJ. So EJ is the jth vector in the basis E. T of EJ, if you look at the coordinate vector for that, that's exactly A1J, A2J, down to AMJ, which is in fact the jth column of the matrix A. So when you look at your matrix A, each column tells you where each basis vector gets mapped to. Right? So that's a very, very, very important fact about what the numbers in the matrix for a linear transformation mean. And let me give an example of how this can be used. There was a previous homework problem that looked at what are called strictly upper triangular matrices. So let A be an n by n strictly upper triangular matrix. So this is a matrix where all the numbers on and below the main diagonal are 0. It's only in the upper triangle that you might have a non-zero coordinate. So for n equal 2, your matrix would have zeros on the diagonal and below, and the only unrestricted coordinate is the number here, which is A12. That's what a strictly upper triangular 2 by 2 matrix looks like. For n equal 3, you have zeros down the main diagonal and below, and it's only these entries, A12, A13, A23. They could be 0, but they can be anything. They could be non-zero. If n is equal to 4, the strictly upper triangular matrix has 4 zeros down the diagonal and below the diagonal are all zeros. And it's only in this upper triangle, A12, A13, A14, A23, A24, A34. These are the only numbers that might be non-zero. So this is the main diagonal. On and below that main diagonal, everything is 0. And it's only in this little triangle above the main diagonal where you could have a non-zero element. Let's look at this matrix, for example. Zeros, so call this matrix A. So So every 3 by 3 matrix represents a linear transformation from the three-dimensional vector space to itself with respect to some fixed bases for those vector spaces. So let's say that this is A. And we have, so let's say A is the matrix for a linear transformation T from with respect to bases E and F. So A times the coordinate vector for V with respect to E gives you the coordinate vector for T of V with respect to F. So if you look at this matrix, A applied to the vector 1, 0, 0 is 0, 0, 0. The first column is the coordinates of the basis vector E1. A applied to 0, 1, 0 is A1, 2, 0, 0. A applied to the third basis vector is the third column, A1, 3, A2, 3, 0. So what this says is if you look at the corresponding linear transformation T, T of E1 is 0. T of E2 only has a first coordinate. It's in the subspace generated just by E1. T of E3, it's a vector where the third coordinate is 0, so it's in the subspace generated by E1 and E2. So T of E1 gets sent to 0. T of E2 is a multiple of E1. That means T squared of E2, which is T of E2, which is T of some multiple of E1, is 0. What about this? T squared of E3, if I apply T to E1, I get 0. If I apply T to E2, I get something in E1. This is in the subspace spanned by E1. So T cubed of E3, if I apply T to this, that's T of some scalar multiple of E1, that's 0. So for this 3 by 3 matrix, A cubed is 0. And there was a previous homework problem that says that if A is n by n strictly upper triangular, then A to the n must be the 0 matrix. And the reason is that A sends the subspace spanned by, let's say, the first k vectors into the subspace spanned by just the first k minus 1 vectors. So as you iterate this matrix multiplication, looked at as a linear transformation, it's mapping the vector space into strictly smaller and smaller subspaces. And when you do it n times, it's 0. So that is a very, very, very useful fact about linear transformations in matrices. It's very nice. So a great deal of linear algebra is spent studying linear transformations. And there are certain words associated, or certain objects associated with a linear transformation. So let T from V to W be a linear transformation. So I claim T of 0 is 0. Let me write this as a little lemma. If you apply T to the 0 vector in V, you get the 0 vector in W. just to emphasize this, I'm going to write a little subscript v and a subscript w. Take the 0 vector in v, t of that is the 0 vector in w. And the proof simply comes from the fact that 0 is 0 plus 0. So t of 0 is t of 0 plus 0. Because t is a linear transformation, this is t of 0 plus t of 0. I don't know what this vector is yet, but it's a vector, so it has an additive inverse. So t of 0 minus t of 0, take a vector and subtract it from itself, you get 0. This is some vector in w, so this minus this, the difference of two vectors in w that are the same is the 0 vector in w. The t of 0 v is t of 0 plus t of 0, and I'm subtracting t of 0 from that. And by associativity, that's t of the 0 vector plus t of the 0 vector minus t of the 0 vector. But this is just 0. This is t of the 0 vector plus the 0 vector in w, which is t of the 0 vector in v. So that kind of long equation is the proof of the statement that a linear transformation always sends a 0 vector to the 0 vector. And there's a second assertion, which is t of the vector minus v is the same as minus the vector t of v. Right? Why is that? So let me give a proof of the second statement. So t of v plus t of minus v, because t is a linear transformation, this is t of v plus minus v. But v minus v is 0. This is t of the 0 vector in v, which is the 0 vector in w. So this plus this is the 0 vector in w, so t of minus v is minus t of v. That's the whole proof of this useful but very simple lemma. So again, let's draw a picture. Here's v, here's w, and t is a linear transformation from v to w. So we have the 0 vector in v, we have the 0 vector in w, and 0 gets mapped to 0. But of course, there can be more things that get mapped to 0. So what we call the kernel of t is the set of all vectors v and v such that t of v is 0. So this is everything that gets mapped to 0. And another very important, I'll call it a lemma, is that the kernel of t is a subspace of v. Proof. Well, we already saw the t of the 0 vector is the 0 vector. So the 0 vector is in the kernel of t. So that's the first property of a subspace, and it's satisfied. Second, if v1 and v2 are two vectors in the kernel of t, then t of v1 is 0 and t of v2 is 0. So t of v1 equals t of v2 equals 0. So t of v1 plus v2, this is t of v1 plus t of v2. That's 0 plus 0, which is 0. So therefore, v1 plus v2 is in the kernel of t. So that's the second property a subspace has to satisfy, is closed under vector addition. And if V is in the kernel of T and C is any scalar, then T of C times V, because T is a linear transformation, T of CV is CT of V. But T of V is in the kernel, so T of V is 0, and any number times 0, the vector 0 is the vector 0. So therefore CV is in the kernel of T. So the subspace, the kernel of T, all the vectors that get mapped to 0, contain 0, is closed under vector addition, is closed under scalar multiplication. Therefore, the kernel of T is a subspace of V. Now, there's also another set that's naturally associated with the linear transformation. Right? Again, we have our picture. Here's V, here's W, here's a linear transformation T from V to W. The 0 of V gets mapped to the 0 in W. Now, every vector V gets mapped to some vector T of V in W. But it's not necessarily the case that every vector in W is the image of some vector in V. So let us define the image of T is all vectors W in the vector space W, such that W equals T of V for some V in V. So over here in W is the subset of all the vectors which actually are the images in V. They have a pre-image. Something is in this red area of W, which is what I call the image of T, if there's a vector V such that T of V is in this red area. That's the image. And our lemma says that the image of T is a subspace of W. So again, what is the proof? We have that T of the 0 vector in V is the 0 vector in W. So the 0 vector in W is certainly in the image of T. So the image of T contains 0. Second, if W1 is in the image of T, then W1 is equal to T of V1 for some V1 in V. That's the definition of the image. And if W2 is another vector in the image of T, then W2 is T of V2 for some V2 in V. So then we look at T applied to the vector V1 plus V2. By linearity, this is T of V1 plus T of V2. That's W1 plus W2. So W1 plus W2 is the image of the vector V1 plus V2. This is in the image of T. So the image of T is closed under vector addition. If W1 and W2 are any two vectors in the image, then their sum is also in the image. And third, if W1 is in the image, and W1 is T of V1, CW1, what is CW1? That's C times T of V1. But by linearity, because T is a linear transformation, this is T of CV1. this is a vector in V. So CW1 is in the image of T. So the image of T is also closed under scalar multiplication. And that proves our theorem. So let's again look at this picture again. I like this picture. Here's V, here's W. Here is the zero vector in V. Here is the zero vector in W. Now, sitting inside of V is the kernel. Let's call this K. The kernel of V. That's everything that gets mapped to zero. And sitting inside of W, so this is the kernel of T. And sitting inside of W is a subspace called the image of T. So I actually have now two vector spaces, V and W. And whenever I have a linear transformation T from V to W that defines a subspace of V, which is the kernel, and a subspace of W, which is the image of that linear transformation. Right? And there is a relationship between these, which is the following. So suppose V be a finite dimensional vector space. So let's say the dimension of V is equal to n. Then, so this is a theorem. Then the kernel of T is a subspace of V, and the image of T is a subspace of W. We know that was what we proved in the previous two lemmas. The theorem says that the dimension of the vector space V is the sum of the dimensions of the subspace's kernel of T plus the dimension of the subspace, the image of T. So this is really a very important theorem. It's one of the fundamental theorems in linear algebra. For finite dimensional subspaces, if you have a linear transformation T from V to W, the dimension of V is the dimension of the kernel plus the dimension of the image. And note, I didn't say anything about the dimension of W. Maybe W is infinite dimensional, but the image of T. So if so suppose we let E1 up to En be a basis for V. Let V be any vector in the vector space V. Say V is summation xi ei. I goes from 1 up to n. So T of V is T of summation xi ei, which is summation xi T of ei. I goes from 1 up to n. So every vector in the image is of the form T of V, and T of V is a linear combination of these n vectors, T of E1 up to T of En. T of V is a linear combination of these n vectors. So these vectors span the image of T. So some subset of them is a basis for the image of T, because we proved that if you have a finite set of vectors that spans a subspace, there's a subset of that set, which is a basis for the subset. Not only spans, but is linearly independent. So the dimension of T of V is the dimension of T of V. The dimension of the image of T is at most n, the dimension of V. So that's just a point I want to emphasize at the beginning. So how can we prove this theorem? So we have V, and sitting inside V is the kernel of T. So the kernel of T is a subspace of V Suppose we let the dimension of the kernel of T be equal to K, because every vector space has a basis. The kernel is the number of vectors in the basis. A subspace has dimension less than or equal to the dimension of the larger space. So if the dimension of the kernel of T is K, that's some number less than or equal to N, which is the dimension of V. So let E1 up to E sub K be a basis for the kernel of T. So we proved a lemma, that is, we said the following. This is a theorem, and we already proved. So this is, I'll say, previous theorem. Let V be a finite dimensional vector space. Say the dimension of V is equal to N. Let E1 up to EK be a linearly independent subset of V. So K is at most N, because N is the size of the largest linearly independent subset of V. There exist vectors EK plus 1, EK plus 2, up to EN, such that the set E1 up to EK, EK plus 1, EK plus 2, up to N, EN, is the basis for V. So we had proved in previous chapter that every linearly independent subset of a vector space can be extended to a basis for the vector space. So let's apply that in this case. So this is a basis for the vector space V, and the first K vectors, these are a basis for the kernel of T. So here we have a basis for V. E1 up to EK is a basis for the kernel of T, and we've extended that to a basis for the rest of V. So we have this basis for the kernel of T, which is E1 up to EK, and then we extend to a basis for V, E1 up to EK, and then we have to add another n minus k vectors, EK plus 1 up to E sub n. So the total dimension of V is n, so here we have n minus k additional vectors. So if we take any vector V in the vector space, V is some linear combination. J goes from 1 to n, x sub j, e sub j. So T of V is T of summation j goes from 1 to n, xj, ej, which is summation j goes from 1 to n, xj, T of ej, because T is a linear transformation. And I can write this as a sum of two sets of vectors. This is the vectors from 1 to k, plus the vectors from k plus 1 up to n. But if you look at these vectors, for j going from 1 to k, ej is in the kernel of T. So this vector is 0. So in fact, this sum is 0. We're just adding the 0 vector to itself k times. So this is just the sum xj, T of ej, j goes from k plus 1 to n. It's this vector in the image of T. Every vector in the image of T is T of V for some vector V in the vector space V. So this says that the image of T is spanned by this set of n minus k vectors. T of Ej, k plus 1 less than or equal to j less than or equal to n. So the image of T is spanned by n minus k vectors. So the dimension of the image of T is at most n minus k. And I'm going to prove the dimension of the image of T is exactly n minus k. So these vectors span the image. I want to show that they are linearly independent. So suppose there exist scalars xk plus 1 up to x sub n such that this linear combination, summation x sub j, T of e sub j, j goes from k plus 1 up to n, is the 0 vector. So we have the 0 vector in W is summation xj, T of ej, j goes from k plus 1 to n, which by linearity, because T is a linear transformation, this is T of summation xj, ej, j goes from k plus 1 to n. But this means that this vector xj, ej, summed from k plus 1 to n, is in the kernel of T. The kernel of T is the set of all vectors that T maps to 0. And the kernel of T has a basis, E1 up to EK. So therefore, summation xj, ej, j goes from k plus 1 to n, must be a vector of the form xj, ej, j goes from 1 to k, which is the same as saying summation j goes from 1 to k, xj, ej, plus summation j goes from k plus 1, and just bringing this over to the other side, n minus xj ej is 0. But E1 up to En, that's a linearly independent set. Those vectors are linearly independent. So all the coefficients have to be 0. So xj equals 0 for all j from 1 up to n. So in particular, from k plus 1 up to n. So therefore, the set of vectors T of Ej, j from k plus 1 to n, is linearly independent. So a basis, we know they span the image of T, so they're a basis for the image of T. So we have that the dimension of the kernel of T is K. The dimension of the image of T is n minus K. So if we add the dimension of the kernel of T plus the dimension of the image of T is equal to n. K minus K cancel, which is the dimension of V. And that is the proof. Now, there are lots of vocabulary words in linear algebra. The dimension of the image of T is sometimes called the rank of T, and the dimension of the kernel of T is sometimes called the nullity of T. So you often see this theorem stated as follows: for any linear transformation T, the nullity plus the rank is the dimension of the domain space V. But that is the proof of the theorem, which is a very important theorem in linear algebra, and definitely something you will be asked to prove on the final exam. So you really need to invest time to understand the proof. Let's look at a couple of very simple examples of linear transformations and their kernels and images. So suppose we let V equal W be R2, and we look at a linear transformation from R2 to R2, and let's say it's the following: T of xy is the vector x0. So check that this is a linear transformation. That's an exercise for you. What is the kernel of this? What does this look like? So here we have a point xy in the plane. That's my V, and it gets mapped to the point x0. That's my T of V. Or I should write this xy, x0. So this is just projection onto the x-axis. So the image of T is the x-axis. And the dimension of the x-axis, that's just a one-dimensional space, the dimension of the image of T is 1. So this red line, that's the image of T. And what is the kernel of T? T of xy is 0, 0. If and only if, what is T of xy? X0 is 0, 0. If and only if x equals 0. The line x equals 0 is the y-axis. So the y-axis is the kernel of T. All the points that get projected onto 0 vertically are the points on the y-axis. The image of T is the x-axis. And so the kernel of T is the y-axis, which is a one-dimensional subspace. The dimension of the kernel of T is 1. And the dimension of R2 is 2. So the dimension of R2 is the dimension of the kernel of T plus the dimension of the image of T. That is 2 equals 1 plus 1. So 1 plus 1 equals 2 is a nice result in linear algebra. Let's look at another example. Again, I'm going to restrict myself to the plane. So define T from R2 to R2 by T of xy is yx. So this linear transformation interchanges the coordinates. So if I have E1, which is 1, 0, T of 1, 0 is 0, 1. So T maps E1 to E2. T of 0, 1 is 0, 1, is 1, 0. So T maps E2 back to E1. Okay. For this map, what is the kernel of T? The kernel of, so xy is in the kernel of T, if and only if T of xy, which is yx, is 0, 0, if and only if x equal y equals 0. So the kernel of T consists of just the 0 vector. And the dimension of the kernel of T is 0. What is the image of T? Well, for every vector xy in R2, xy is T of yx. So every vector is in the image of T. The image of T is all of R2. So the dimension of the image of T is equal to 2. So the statement that dimension of R2 is dimension of the kernel plus dimension of the image is just the statement 2 equals 0 plus 2. Okay, so that's a confirmation in this case. Let's look at a slightly more complicated linear transformation. Suppose we have T from R2 to R2 defined by T of xy is x plus 2y, 2x plus 4y. So what is the kernel? So xy is in the kernel of T if and only if T of xy is the 0 vector, which is T of xy is this, if and only if x plus 2y, 2x plus 4y is the 0 vector. So if and only if x and y are solutions of the equations x plus 2y equals 0, 2x plus 4y equals 0. And this is the same as saying if and only if the solutions of that equation, there are infinitely many, x equals minus 2y. So if and only if the vector xy is minus 2yy, or y times the vector minus 2, 1. So the kernel of t is the set of all scalar multiples of the vector minus 2, 1. So the dimension of the kernel of t is 1. This is a one-dimensional vector space. It's all scalar multiples of this one non-zero vector. So let's draw a picture. The kernel is all vectors where x equals minus 2y, or if you like, y equals minus a half x. That's a line through the origin, the slope minus a half. So this line is the kernel of t. Something gets mapped to 0 if and only if it's on this line. What is the image of t? It's the set of all vectors of the form t of xy for xy in R2. That's all vectors of the form x plus 2y, 2x plus 4y for all x and y in R2. But I can write this as follows. This is, I can factor out x plus 2y times the vector 1, 2. Because this is x plus 2y, and this is 2 times x plus 2y. So it's all scalar multiples, 1, 2, by numbers of this form, which are just all numbers. This is a set of all x times 1, 2 for all x in R2. So the dimension of the image of t is also 1. And so our theorem again comes down to the fact that 1 plus 1 equals 2. The set of scalar multiples of the vector 1, 2, there's the vector 1, 2. It's just this blue line. This blue line is the image of t. So every vector gets mapped to something on the blue line, and every vector on the red line gets mapped to 0. Okay. So there's examples of computing the kernel in the image. It's very important. Let me make just a couple of other quick remarks. Suppose t from v to w is a linear transformation. And suppose we let k be the kernel of t. So let v1 and v2 be in v. So t of v1 equals t of v2 if and only if t of v2 minus t of v1 is 0, which is the same as saying v2 minus v1 gets mapped to 0. So if and only if v2 minus v1 is in the kernel of t. So if the kernel of t is just the 0 vector, then t of v1 equals t of v2, if and only if v2 minus v1 is 0, or if and only if v1 equals v2. So such a function is called one-to-one. T is one-to-one in this case. What this means is, here is v, here is w. T is mapping from v to w. v1 and v2 are two vectors in v. If they get mapped to exactly the same point, then in fact they have to be the same vector. So if the kernel of t is 0, then any two different vectors must be mapped to two different vectors in w. That's not the case if the kernel of t is non-zero, because in that case there's some vector in the kernel of t different from 0, and it as well as 0 gets mapped to 0. So a function that maps different elements to different elements is called one-to-one. So we have a theorem that says t is one-to-one if and only if the kernel of t consists of just the 0 vector. So that is a useful fact about linear transformations. There are two other linear transformations that are very important because they're basic and they're actually kind of simple. So let's consider R2 and a function from R2 to R2, a linear transformation. Let me call this R sub alpha. Alpha is an angle. So if you take a vector v in the plane, R alpha rotates that vector by alpha radians. So this is rotation around the origin by alpha radians, right? We always use radian measure. 2 pi is equivalent to what you would used to call 360 degrees. And rotation is a linear transformation. What is the matrix for the rotation function? Let's see. If we take the unit vector E1, this is the unit circle, if it's rotated by an amount alpha, it gets sent to this point, and this is cosine alpha, sine alpha, right? So you have to remember elementary trig. If you take the unit vector, rotated alpha radians around the circle, this is actually the definition of cosine and sine. So this rotation R alpha of the vector 1, 0 is the vector cosine alpha, sine alpha. If you take the other basis vector 0, 1, E2 equals 0, 1, you rotate this alpha radians around the circle, and the cosine and the coordinates of this point are sine alpha minus cosine alpha. So R alpha of 0, 1 is sine alpha minus cosine alpha. So the matrix for rotation by alpha is cosine alpha, sine alpha, oops, I'm sorry, this is minus sine alpha, it's negative plus cos minus sine alpha, cosine alpha. And the determinant of this matrix is cosine squared alpha plus sine squared alpha equals 1. So if you have rotation by alpha radians around the unit circle, that's a linear transformation with this matrix. There's another geometrically very simple and important linear transformation in the plane, which is the following. Instead of a rotation, we can look at a reflection. So in the plane, here's the line L alpha. It's the straight line that makes an angle alpha with the positive x axis. And S alpha is going to be reflection through the line L alpha. What that means is if you take a vector xy, you draw the perpendicular to this line and then continue the same distance on the other side, and this is S alpha of xy. So you take your vector and you reflect it through that line. How can we work out the matrix for this? So let's remember some high school geometry. Here we have a right triangle. Here we have a right triangle. They have the same side here, and these two sides are the same. So these are congruent triangles. Let's see. Let me call this xy, and this is reflection, so the picture is easier. Suppose this angle is theta from the origin to my vector. So this vector has polar coordinates r theta. This is theta. This is alpha minus theta. This is alpha minus theta. So when you reflect, S of xy has polar coordinates. The distance to the origin hasn't changed, but the angle, instead of being theta, is alpha plus alpha minus theta is 2 alpha minus theta. So let me draw a better picture of this. I'm reflecting through this line L alpha. So this angle is alpha. And I take my vector V, whose polar coordinates are going to be r theta. That means this distance is r and this angle is theta. And when I reflect it, I get S alpha of V. The distance is the same, distance to the origin. The length of the vector hasn't changed. But this angle is now r 2 alpha minus theta. So What are the coordinates of this vector in rectangular coordinates? This is going to be r cosine theta, r sine theta. What are the coordinates of this vector? The rectangular coordinates. It's going to be r cosine of 2 alpha minus theta, r sine of 2 alpha minus theta. What is that? So we have double angle formulas. Cosine of 2 alpha minus theta is cosine 2 alpha cosine theta plus sine 2 alpha sine theta. And the sine of 2 alpha minus theta is sine 2 alpha cosine theta minus cosine 2 alpha sine theta. So this is equal to, let's see, r, so r times this multiplied by r. R cosine theta is x. This is x sine 2 alpha minus y cosine 2 alpha. And this, if I multiply by r, is x cosine 2 alpha plus y sine 2 alpha. So this is all done very neatly in the notes, so I'm sorry if this is sort of illegible. So S alpha of xy is going to be x cosine 2 alpha plus y sine 2 alpha, x sine 2 alpha minus y cosine 2 alpha. That's the vector, the matrix cosine 2 alpha, sine 2 alpha, sine 2 alpha minus cosine 2 alpha. So the matrix for reflection is given by this matrix. And the determinant of this is minus cosine squared 2 alpha minus sine squared 2 alpha is minus 1. So these are two fundamental examples of linear transformations in the plane. A rotation around the origin by alpha radians that has a matrix which has determinant 1, and reflection through a line through the origin in the plane, and that has determinant minus 1. So these are important linear transformations to know. And that's it for today.